Oceanographers. Today we're going to be talking about ocean circulation patterns in the global ocean system. We learned about air-sea interactions last time, and before that we talked about the density structure of ocean water. We're going to put all that knowledge together to look at ocean current patterns and what controls different kinds of ocean patterns, current patterns in the global ocean system. I put up this image to begin with to show you how the Gulf Stream behaves as part of the global circulation system in the oceans. You see the warm Gulf Stream coming out of the Gulf region and flowing north pretty close to the eastern shoreline of the North American continent, and then cuts across the central Atlantic Ocean, meandering and forming a bunch of eddies, and then basically it starts splitting into two parts. One goes to the north and becomes the North Atlantic Drift, and the other one goes to the east towards the Canary Islands. We'll talk about the Gulf Stream a little bit in detail later on, but here's today's roadmap about what we're going to discuss. We're going to look at the ocean current systems, and we look at the currents as surface currents and deep currents. And the surface currents are driven by wind patterns, and we talked about that, but we're going to get into it a little bit more in detail. So looking at the surface currents, we'll be talking about different gyres and gyre systems in different ocean systems, and there are several phenomena that affect the gyre systems, like the Ekman spiral and geostrophic flow. And we're going to be talking about also upwelling and downwelling zones and what controls these particular current systems in the oceans. Then we're going to look at El Nino and La Nina events, very important because they really affect the global climate for several years in a row when they kick in. And we're going to talk about what really controls the El Nino events and why they develop. And then we're going to talk about the density-driven deep ocean currents, and we're going to look at the conveyor belt circulation at the end. So ocean currents, we have two categories of ocean currents. Surface currents, strongly affected by major wind belts of the world, and these currents move the ocean water in a horizontal fashion, and usually these surface currents operate right above the pycnocline, about the first 1 kilometer of ocean water, and affecting nearly 10% of global ocean water. Deep currents, on the other hand, affect nearly 90% of ocean water, and they operate below the pycnocline, so below that 1 kilometer depth from the surface of the oceans. And the major force behind these deep currents are the density differences in ocean water, and we're going to get into that in detail later on. The deep currents are much larger in terms of their extent, and they're also slower than surface current waters, but they're extremely important because we consider them as the temperature controlling factor for the global climate. So we just said that surface currents closely follow global wind patterns, and if you remember this diagram, we looked at a different one last time, showing the wind patterns and wind belts, and we're looking at here the between the equatorial zone and the 30-degree north and south latitudes, we have the trade winds. In the northern hemisphere, these trade winds blow from the northeast to the southwest, and in the southern hemisphere, they blow from southeast to the northwest. And then when they converge towards each other, they form what we call the intertropical convergence zone, which results in significant upwelling along the equatorial belt. And that is a very important phenomenon particularly in the Pacific Ocean, and we'll talk about that later on as well. And then going higher uh, in the northern and southern hemispheres, higher latitudes between 30 and 60 degree north and south latitudes, we have the westerlies. And as the name implies, these winds blow from the west, southwest to the east, northeast in the northern hemisphere, and also in the southern hemisphere. They're blowing from the west to the southeast. Okay, so trade winds are extremely important for setting up the gyres and the surface currents in the oceans. And early seagoing people recognized the significance and the existence of these winds, particularly in their adventures into the Atlantic Ocean. In Middle English in the early 13th century, trade meant path or track. And the early sailors, particularly traveling towards Greenland, to the other side of Greenland, to find for places for better farming during the ice ages, they actually took advantage of these wind systems. And by the 18th century, the importance of the trade winds was particularly well understood, and particularly the British Empire took advantage of these trade systems, trade wind systems, and England's merchant fleet used the trade winds very effectively crossing the Atlantic Ocean, and also colonizing different parts of the world by taking advantage of these wind systems. So they had a very good understanding of these wind patterns and their effect on the ocean current systems. So by the 18th century, because of this significant trade put together by the British fleet, the trade was also meant in English commerce. And so, to some extent, trade winds basically ushered in the colonial forces across the oceans, particularly by the British, Portuguese, and Dutch. So trade winds played a significant role in European empire building and thus modern political geography. On this map, you're looking at the surface ocean currents in the Atlantic Ocean. And you realize that trade winds between the equatorial zone and the 30-degree north and south latitudes blow surface ocean currents to the west. Here in the northern hemisphere, you see that trade winds blowing the ocean surface to the west, and in the southern hemisphere, again from southeast to northwest, these are the strong southeast trade winds. And the prevailing westerlies between the 30-degree and 60-degree latitudes blow surface ocean currents to the east. So you're looking at in the northern hemisphere, these are westerlies, prevailing westerlies that we saw right here. And in the southern hemisphere, those westerlies basically flowing from the west to the southeast, like we see in this diagram of the wind belts. So collectively, the trade winds and the westerlies set up these ocean surface currents in both hemispheres, and we will see very shortly that these two surface currents are part of a significant phenomenon that we call subtropical gyre system, and we have 5 of them in the global ocean system. But the surface currents are affected by some other forces, not just the wind patterns. Distribution of the continents strongly affects how these ocean currents and their gyre system operate, because they could be strong barriers in front of these current systems. Coriolis effect that we talked about last time also affects the ocean currents, and we'll have several examples of that very shortly. And gravitational force, of course, plays a major role, and friction with wind flows, and a new term called Ekman transport and Ekman spiral also plays a significant role. We're going to get into this Ekman spiral very shortly. But let's take a look at the wind-driven surface currents a little bit in detail. So we're looking at the global ocean system. We're looking at February-March configuration of the ocean current systems globally. And the red arrows indicate warm currents, and the blue arrows reflect the cold currents in all these different ocean systems. So we have all these large gyre systems centered in the subtropical areas in each and every ocean except in the Indian Ocean, where we have only one gyre, as we'll see very shortly in detail. And so 1, 2, 3, and 4, 5 gyre systems, and they're all bounded by different surface currents. So all these subtropical gyres have equatorial currents. These currents are driven by trade winds, as we just talked about. And then the western boundary currents on the west side of, for example, the subtropical northern gyre in the Pacific Ocean. This is the western boundary current in the Atlantic Ocean, and it's the Gulf Stream, as we looked at the image earlier. And then we have the northern and southern boundary currents capping bounding the gyres in the north and in the south. And then we have the eastern boundary currents, like the Canary Current in the Atlantic Ocean, coming from higher latitudes and bringing very cold water. So in general, these western boundary currents are always very warm, and they bring warm waters and warm climate to the surrounding continents. And the eastern boundary currents are always very cold and bring cold air and cold climate to the surrounding continents. That's why Northwest Africa is always cold and dry, like in Morocco and so forth. Equatorial countercurrents are the currents that flow from west to east, and these currents flow in the opposite direction to the equatorial currents set up by trade winds, and usually driven by gravitational flow from west to east. Here is one, the eastern countercurrent in the Pacific Ocean, and then here is the eastern countercurrent in the Atlantic Ocean, and there is one also in the Indian Ocean. There are also subpolar gyres set up in a much smaller scale adjacent to the much larger and very powerful subtropical gyre systems. So let's take a look at these gyres a little bit in more detail. They form these large circular moving loops of water, and we have 5 of them each, 2 in each of the main oceans, the Pacific Ocean and the Atlantic Ocean, and there is one in the southern Indian Ocean, because the Indian Ocean is basically a southern hemisphere ocean. All these gyres, again, centered around mid-latitudes, about 30-degree north and south latitudes, and that's why we call them subtropical gyres, and they are extremely important in regulating the temperature conditions in the adjacent continents. The smaller subpolar gyres exist in higher latitudes, and they rotate in the opposite direction to the adjacent subtropical gyres. Here is the northern subtropical gyre in the northern Atlantic Ocean, flowing in a clockwise fashion, and you see the subtropical subtropical gyre in the North Sea off the coast of Greenland and Baltic continent in the north. It is flowing in the counterclockwise fashion adjacent to the subtropical gyre to the south. One of the important phenomena in the ocean current system is called Ekman spiral. And Ekman spiral describes the speed and direction of flow of surface waters at different depths going into the ocean. And two things control Ekman spiral, its direction and magnitude. Winds, of course, as we just discussed, very important, and of course the Coriolis effect. Remember, the Coriolis effect is the deviation of all items not attached to the Earth, like air masses and airplanes and ocean current systems. They deflect to the right in the northern hemisphere, but they deflect to the west or to the left in the southern hemisphere. The Ekman spiral and the related phenomenon was first recognized by a Swedish scientist, one Wolfred Ekman, who lived between 1874 and 1954. And Ekman used to be sailing in the North Sea very often, and he realized that sailboats and ships would actually would not follow the permanent prevailing wind direction at sea, but rather they would deflect to the right a little bit, and right of the strong wind system. And he looked into this phenomenon and he came up with the concept of Ekman spiral. So Ekman spiral is controlled by the Coriolis effect very strongly. You're looking at in this diagram, this is a three-dimensional diagram with a cross-section of what happens to the water in the ocean as you go deeper down to 100 meters. On the right-hand side, you're looking at the map view of this phenomenon. And let's take a look at this diagram on the left. You have the prevailing wind blowing in this direction, as the green arrow shows. And anything at the surface of the ocean, like the water, starts basically moving in the direction about 45 degrees to the right of this prevailing wind direction in the northern hemisphere. And this is strictly an artifact of the Coriolis effect. But in the southern hemisphere, the opposite takes place, and this deflection takes place to the left of the prevailing wind direction. And as you go deeper into the water in the ocean, more deflection and more turning further to the right takes place. And you see that these arrows, as you go deeper into the ocean water within the 100 meters, is basically rotating in a clockwise fashion, and the water is basically moving in these directions of different arrows. And you see that the magnitude of these vectors is getting smaller as you go deeper and deeper. And by the time you get down to 100 meters, actually the ocean current system at 100-meter depth is going exactly in the opposite direction to the prevailing wind at the surface, the atmospheric wind pattern. And then the ocean current is going in the opposite direction. So this whole phenomenon is called a spiral, an Ekman spiral. In the map view, you're looking at the prevailing wind blowing up in this direction, and the Ekman spiral is shown by these different colored arrows, and finally that is the deepest current, exactly opposite direction to the prevailing wind. And so This is what we call the Ekman transport, about nearly 90 degrees to the right of the prevailing wind in the northern hemisphere. So Ekman transport is about 90-degree transport from the wind, prevailing wind system of the surface current patterns. There is another phenomenon related to subtropical gyres. We call them geostrophic flows and related western intensification. Here you're looking at a profile of what we call geostrophic flow, and I'm going to explain that in a moment. And this is the map view, or looking from an airplane down to subtropical gyre, and this is how it looks like in terms of its internal structure. So subtropical gyre system, like the one in the northern hemisphere in the Pacific Ocean, has this lens, contact lens shape with a raised sea surface. So geostrophic flow, and the gyre system has this little bubble up raised surface. And the center of this gyre is shifted to the west because of the rotation of the Earth. Because of the rotation of the Earth and the related centrifugal forces, this is not a perfectly symmetrical gyre. The west side has a steeper slope, whereas the east side has a very gentle slope. And so on this surface, bubble surface, we are looking at an actual geostrophic flow shown by this dashed line. So we have the path of the ideal geostrophic flow following the contours of this hill. But two things happen. One is the effect of the Coriolis force, and therefore deflecting to the right in the northern hemisphere. The other thing is, of course, that when you have a raised surface, it has the gravitational potential energy, so the water higher up will have tendency to flow downhill. So the combination of Coriolis and the gravity makes this geostrophic flow going in this direction. So you're looking at, in the map view, a geostrophic flow within a subtropical gyre system. These are the elevation lines, and you see that they're very close to each other. But on the east side, the elevation lines within the east side of this geostrophic flow, the distance between these lines is pretty wide. So there is a compression on this side in that geostrophic flow, and as a result we have very narrow and very strong currents on the west side of the subtropical gyres and on those geostrophic flows. But on the east side, the eastern part of the component of the geostrophic flow and the subtropical gyre system has a much wider cross section and very sluggish and slow. Okay, so western boundary currents, as a result of what we just discussed in terms of geostrophical flows, western boundary currents of all subtropical gyre systems are very fast, narrow, and they are very deep, and they're also very warm. They are warm because they're coming from the tropical parts of the ocean systems. If you look at the Gulf Stream, for example, coming from the very southern latitudes, so very warm water going on the west side of the Atlantic Ocean. And if you look at this particular western boundary current coming along the Japanese islands, Kurashiro current, and it's also a very important current system bringing lots of typhoons to the Japanese islands, particularly in the summertime, and it's extremely warm. The eastern boundary currents are cold, and here is that Canary Island Canary Current, which is very cold, very wide, and it basically affects the temperatures and the climate in southern Spain, in the Iberian Peninsula, and northwestern Africa. So these currents strongly affect the climatic patterns in the adjacent surrounding continents. When you have warm currents, these warm currents bring warm air to the region, and also they bring high water vapor. And so they set up lower pressure systems, and as a result, we have very humid and warm coastal climate. That's why in the Philippines, in Japan, we have warm climate pretty much throughout the year, and it becomes even much more pronounced in the summer times in Japan. That's why Tokyo always gets very strong typhoons and rainstorms throughout the summer. The same thing happens on the east side of the North American continent, and we have these warm currents like the Gulf Stream bringing humid and warm air and temperatures to the continent. In fact, the Gulf Stream carries that warm air all the way across the Atlantic Ocean to the British Isles and the western part of the Baltica continent, and making the winter months much more tolerable in those places. Cool currents operating on the east side of the gyres are essential in terms of cooling the air and setting up high pressure systems. And so the cold air that comes with the cold ocean currents have low water vapor, and so very dry coastlines as we have in the southwestern United States and off the coast of Baja Peninsula and the Sonora Desert in Mexico. Upwelling and downwelling are two important phenomena in the oceans, and they're related to, again, surface currents and what happens between the atmosphere, lower atmosphere, and the ocean surface. So you're looking at the diagram here on the right-hand side. We have surface winds blowing away from the offshore, from the land towards the ocean. And we'll talk about this later on, when and how this kind of wind system persists. When we have these surface winds pushing the surface water away from the shoreline, the warmer surface water moves offshore. And of course, when you move that water, you have to replace it with water. And as a result, deeper, colder, and nutrient-rich water, deep water, rises up from depth and beneath the surface and replace the surface water. So this phenomenon is called upwelling of colder water to the surface. This is extremely important because this cold water brings lots of dissolved oxygen in the water, and also lots of nutrients like phytoplankton and zooplanktons into the shallow waters. And as a result, fisheries thrive in these kinds of upwelling zones, like the Peruvian fisheries. Normal years with the right pressure systems exist in the atmosphere, we have a strong upwelling of the coast of northwestern South America. And the economy of the entire country of Peru largely depends on this upwelling system and the fisheries and the health of these fisheries. So upwelling can actually produces high productivity and abundant marine life in the oceans. And downwelling, on the other hand, is plunging of the surface water down into deeper ocean. So it moves warm, nutrient-depleting surface water into deeper ocean. And when this happens, there is a lack of nutrients in the ocean waters, and fisheries may collapse. So we're looking at two diagrams here. The one on top is about upwelling, and we talked about that. So when you have southerly winds, for example, off the coast of Peru and South America, we have trade winds blowing from southeast to the northwest, and this wind system sets up an ocean circulation at the surface, so that with the combination of the winds and Ekman transport, the surface water, warm surface water, is pushed away from the continent, and the nutrient-rich cold water comes up to replace it, and that basically causes what we call upwelling. And this is usually what takes place off the coast of Peru and northwestern part of the South American continent. But occasionally this may change, particularly when the air patterns and the wind systems become modified, particularly during El Nino years. So you see the strong wind now is coming from the north, because the trade winds are relaxed or diminished because of the pressure changes over the Pacific Ocean. So this northerly wind now coming up from the north offshore of South America, and the combination of Ekman transport and Ekman flow pushes the warm surface water up against the continental margin, and then we have that surface water has nowhere to go but dive in deeper into the water, and that causes downwelling. And downwelling, of course, is extremely harmful for marine life, because it diminishes all the nutrients in the surface water. There are several other upwelling systems. They're all locally set up, and they depend on different factors, like whether you have any geological anomalies on the seafloor, like seamounts and so forth, in shallow waters for seafloor obstruction, or sharp bend in coastal geometries, setting up local upwellings. But the most important upwelling, besides the regular wind-generated upwelling patterns, is the equatorial upwelling. So you have the trade winds coming in from the northeast to the southwest, and you have the trade winds coming from southeast to the northwest. And these two trade wind systems converge along the equatorial zone, and we call that the intertropical convergence zone. When you have these two wind systems converge, they basically blow the ocean surface waters in opposite directions, and that results in local upwelling about 100 or 150 meters deep into the ocean. And this actually is very important, because the equatorial waters, of course, are very warm, and normally they wouldn't sink because they're much lighter than colder water. But because of the strong winds parting these ocean surface waters, you have upwelling cold water replacing the displaced surface water, and that causes equatorial upwelling, and also brings in oxygen-rich and nutrient-rich deep waters to the surface. And in otherwise pretty dismal organic life in the equatorial zone, we have a very narrow band of upwelling with thriving life and organisms. Okay, so You probably heard about El Nino and El Nino events, which happen every 7 to 8 years, but it could be up to 10 years. So it's periodic, and it's all about this warm surface current in the equatorial eastern Pacific that affects the coastal climate and, in fact, all the way to continental interiors. And it happens about Christmas time. So the name comes from Spanish El Nino, Christmas child. And for the first time, Peruvian fishermen realized that about Christmas time, relaxing of the wind systems and lots of rain, and then, of course, no good fishing. So they came up with this term, and subsequently, by scientists, this event was confirmed. And now we know that it is part of the global climate system and strongly affecting the continental climate as well as the ocean circulation patterns. So it's all about the change in the pressure systems, atmospheric pressure systems between the west and east on both sides of the Pacific Ocean. And we call that the southern oscillation, the changes in the pressure system on the west and the east of the Pacific Ocean. And ENSO, El Nino Southern Oscillation, describes a combined oceanic atmospheric disturbance that happens periodically. So normally, we have a low pressure system sitting near the northeastern part of Australia, and this is Papua New Guinea. And on the east side of the Pacific Ocean, along near the equatorial zone, we have a high pressure system in the atmosphere, creating a cold system off the coast of South America. So when you have warm air in the west, to the north of Australia and Papua New Guinea, this low pressure system dumps lots of rain, and precipitation rate becomes very high normally. And this moist air with rainfall start rising, and then once the precipitation takes place, it becomes dry and starts moving to the east, to the eastern part of the Pacific Ocean, and becomes much cooler. And then the cool and moisture lacking air sinks off the coast of South America in this high pressure system, and that creates a very cold and dry weather off the coast of South America. And this pressure gradient between the west and the east, between the low pressure in the west and the high pressure in the east, actually fuels much stronger trade winds. So we have these strong southeast trade winds blowing from the southeast towards the west and northwest, towards the equatorial zone. And these trade winds then set up this upwelling, a combination of trade winds, Ekman transport, and Coriolis effect collectively forming this strong upwelling of the coast of the northern part of South America. So that's usually what it takes place across the Pacific Ocean. And notice that we have relatively warm water mass near the surface, a pretty well-defined thermocline, and underneath we have in blue cold water. So this normal regulation of the high pressure and low pressure system across the Pacific Ocean is called Walker circulation. And a British scientist discovered this and wrote a paper about this for the first time, Sir Gilbert Walker. And to give him credit, since then, since 1870s, early 1940s, we call it the Walker circulation. So these are the normal conditions, the Pacific Ocean water. But what happens when this pressure system, atmospheric pressure system, all of a sudden changes. So here is a diagram that shows now that the pressure systems we looked at earlier completely switched around. So we have the high pressure system sitting on above the Australian subcontinent and Papua New Guinea in the western equatorial Pacific Ocean. And on the other hand, to the east, we have a low pressure system up the coast of Central America and northwestern part of South America. So the warm water brought in by the trade winds earlier pile up against the Australian continent and Papua New Guinea. And when the high pressure system of the coast of South America weakens, reducing the pressure gradient, pressure change between the eastern and western parts of the Pacific Ocean, these trade winds diminish. So we see that there are no trade winds blowing from southeast to the west. And this warm surface water that got piled up against the Australian continental margin and Papua New Guinea starts basically flowing back across the Pacific Ocean towards the South America. So we have this warm surface water now flowing backwards towards the South American continent. And this event usually starts about mid-fall, September in the west, and reaches South America by late December, about Christmas time. And that's why the fishermen call this event Christmas Child or Christ Child, El Nino. And when you have this kind of atmospheric pressure system completely switched around from normal times, with warm water piled up against the South American continental margin. We have a low pressure system with lots of precipitation and rainfall, and the sea level may go up by as much as 20 centimeters or 8 inches, piling up against the South American continent, and water becomes about 10 degrees Celsius warmer. And when that happens, the fisheries here, of course, collapse because warmer temperatures mean lack of nutrients, and lack of nutrients mean no robust fish life in the water off the coast of South America. And this is absolutely detrimental to the economy of the South American continents in the north, particularly Peru. And so coastal upwelling stops, nutrients disappear, and fisheries collapse when El Nino happens. You notice that this low pressure system with lots of precipitation affects not only Central America and South America, but also Southwest America. So we get lots of rain in Arizona, New Mexico, Nevada, Southern California, and in fact, the temperatures and precipitation patterns may change all the way inland to Southwest Ohio. So El Nino is not permanent. It lasts for 12 months, 8 to 12 months, and then it is basically replaced in some years by completely opposite conditions in the equatorial South Pacific Ocean. And we call that the cool phase of ENSO, the Southern Oscillation, and it's exactly opposite to El Nino, and so the scientists have called it La Nina, and La Nina for female child. So the El Nino conditions are a little bit similar to the normal conditions, except they're much more severe in the sense that we have now a very strong high pressure system set up in the eastern equatorial ocean off the coast of South America, and in fact also North America, southern North America as well. And the low pressure system off the coast of Australia and Papua New Guinea very strong. So there is the strong pressure gradient across the equatorial Pacific Ocean, and there are strong, very strong trade winds blowing from the southeast to the west northwest, causing strong upwelling. And you realize that with this strong upwelling, this thermocline, a zone of rapid change in temperatures, pushed up, so it becomes very shallow close to the South American continent, unlike what we saw during the El Nino years, pressed down because of the downwelling. And so we have very strong and cold winds in Peru on land, very harsh winters, and El Nino and La Nina events can occur at irregular periodical intervals for about 2 to 7 years. In Australia, the 2010 La Nina event caused enormous amount of damage because of catastrophic floods in northeastern part of the Australian subcontinent. And if you remember, this past winter in 2020, we also had extremely strong wildfires in Australia because of the opposite effect of La Nina. You're looking at the map view of the equatorial Pacific Ocean during El Nino in January 1998 and La Nina periods in January 2000. So the time difference between these two maps is about 2 years exactly, and you're looking at what the ocean surface water temperatures look like. Here is the scale. You go from minus 5 degrees Celsius with deep blue to crimson red blue plus 5 degrees Celsius. So in a typical El Nino year, you see this very strongly developed warm ocean water, surface water, occupying much of the central Pacific Ocean along the equatorial zone. There is a big tongue of warm water extending all the way to the other side of the Pacific Ocean, bringing extremely warm temperatures up against the South American continent. And one of the worst El Nino events in the history of the Earth was, recorded human history, was January 1998, and that affected all the continents and all the ocean systems, corals around the world quite significantly. 2 years after that, the pressure systems completely switched around and there was a strong La Nina event. So take a look what happened to the ocean surface temperatures in January 2000, and you see a very cold surface water extending all the way from the eastern equatorial Pacific Ocean all the way to the west. So that brought lots of cold temperatures to the Western Pacific and many of the islands in the Western Pacific. Scientists keep track of El Nino and La Nina events because these events strongly control the climatic patterns in the Earth and also affect the global climate patterns. And usually recurrence interval for El Ninos is about 2 to 12 years, with increasing global warming and warmed up ocean water. This interval is actually getting less and less in recent years. So we're going to be seeing much more frequent El Nino events into the future. And this diagram shows the ENSO index, calculated based on atmospheric and oceanic factors. And you're looking at basically El Nino events marked in red and La Nina events marked in blue on this diagram. Numbers deviating from 0 on this reference line reflects stronger El Nino or stronger La Nina events. So if you look at this diagram, you're going to see El Nino event in about 1952 followed by a very strong La Nina event in 1955, and then another El Nino kicked in about 1957-98. And periodically, you're seeing every 7-8 years strong El Nino events. So there was one El Nino event that took place in about 1983, 1984. That was really devastating, and the last one in 1998 caused incredible damage around the world. Um, um, Very strong El Nino events certainly affected jet streams that we talked about last time, and produce unusual weather conditions around the globe. Mostly dry um, regions around the world would end up with high precipitation and some um, um, moist moisture, and warm places end up with basically getting extremely dry and cold. If we look at this map around the world with different symbols, we see how El Nino events can affect the both ocean and the continents. So we have marine life impacted very strongly all the way around the western coastline of the South American continent, of course, along the west coast of the North American continent as well. Significant coral reef damages take place during El Nino events. The Galapagos Islands and the southwestern Pacific Ocean islands, and then, of course, along the coast of Australia, also the coral reefs have been damaged during El Nino events. Tropical storms form during these El Nino events, causing significant damage, but probably one of the most profound damages is the drought brought in by El Nino events, both in Australia and in Indonesia and the Philippines. And of course, we also have the same phenomenon taking place in Mexico, in India, and Africa as well. And tropical fires usually follow these kinds of extremely dry seasons. Bird lives are impacted in wetlands, and strong coastal erosion can take place when you have the warm water piling up against the continental shoreline and cause an enormous amount of erosion and weathering. So El Nino could be extremely damaging both in the oceans and on the continents. Monsoon systems are also part of the surface currents in the oceans. We briefly talked about monsoons when we talked about the atmospheric circulation patterns. And here is a map that shows the Indian Ocean, Australia to the east, Africa, the Arabian Peninsula, and the Indian subcontinent right there. And this is the subtropical gyre system in the southern Indian Ocean. And in the wintertime, the land over India cools off very rapidly because, as you remember, rocks have very, very low heat capacity. They're not good conductors of heat. So in the wintertime, with cooling atmospheric conditions, the air pressure over India is cold and high pressure system, but the water in the Indian Ocean is still nicely warm in the wintertime. So there's a low pressure system residing over the Indian Ocean to the southwest. So because of this pressure gradient now, and remember, atmospheric winds always blow from high pressure to low pressure system. So we have these strong winter monsoon winds blowing from the continent into the Indian Ocean, and that basically brings very dry weather and almost no precipitation in the wintertime in the Indian subcontinent. And notice that these strong winds are affecting the subtropical gyre in the Indian Ocean. So this is the Somali Current, which is very important for the people in Somalia, Saudi Arabia, and further south in Africa because of the what this Somali current normally does, that is upwelling. But in the wintertime, we have this counterclockwise now ocean current off the coast of the northern the African Horn, as we call it here, and these are different current systems that make up the subtropical gyre system in the Indian Ocean. But in the summertime, when the land actually over Asia warms up very quickly during the summertime, the warm air rises and forms this low pressure system. But on the other hand, the Indian Ocean water is still pretty cold because it takes lots of time to warm up the ocean water late into the summer. So that sets up a high pressure system in the Indian Ocean to the west, southwest. So the wind starts blowing from southwest to the east northeast, and from cooler ocean towards the warmer land. And this wind system brings lots of precipitation because these winds coming from the southwest over the Indian Ocean picks up lots of moisture, and then once they hit the continent, and particularly higher grounds, they dump that as precipitation. So that's why we get the summer monsoon in the Indian subcontinent, and that is incredibly devastating in places like in southern India and in Bangladesh to the east. But on the other hand, the entire agricultural system of the Indian subcontinent relies on this monsoon system. So they expect that summer monsoon, and when it slacks off and diminishes, then the Indian economy also goes into deep trouble as well. But notice what happened to the gyre system now in the Indian Ocean. The Somali current, which was flowing to the southwest in the wintertime, now reversed itself and is actually flowing to the north and northeast. So as it does that, it creates this really cold system and upwelling, and this upwelling of extremely cold water from deeper in the ocean brings in lots of nutrients, and the Somalian basically margin is one of the most important fisheries in the whole world, a very diverse and very thriving life during the summer times off the coast of Somalia because of the summer monsoons. So we're done with the surface currents, and we're going to take a look at deep ocean currents. And we said earlier that deep ocean currents are controlled by two things: temperature of seawater and the salt content of seawater, and that is the salinity. So, not surprisingly, the deep currents are always set up and originating from the polar regions, where the temperatures are always cold and the surface waters become extremely cold, particularly in winter times, and cold water is dense and it sinks. But also, when the cold surface water starts forming ice, the salt in the seawater cannot get into the crystal system of ocean water and the crystal system of ice. And as a result, when the ice forms at sea, the salt is left behind. And as a result, this water here becomes relatively enriched in salt when larger and larger ice forms at sea. And as a result, this water becomes not only cold but also extremely salty. So then it sinks. So we're looking at a north-south profile of the Atlantic Ocean, for example. You see a bathtub looking nature geometry of the Atlantic Ocean, and we have basically extremely cold polar waters, cold and salty. They sink both in the south near the Antarctic continent and in the north near Greenland and Iceland and Baltica. And so if you look at this profile, you'll see that in the central Atlantic Ocean, you have extremely warm surface water because of the high solar radiation warming up this water here in equatorial and subtropical regions. And also because of high rates of solar radiation, we have high rates of evaporation, and therefore the salt content of the ocean water becomes also high in the central Atlantic Ocean. So, but mostly because it's extremely warm, it is relatively light and stays at the surface. Then there's this intermediate water mass coming from about 30 to 60 degree north latitude, where the temperatures are relatively cooler. And so this water basically sinks underneath the Gulf Stream or the warm surface water and makes the intermediate Atlantic water mass. And you see that his big tongue of this green intermediate water sandwiched between the warm Gulf Stream and the North Atlantic deep water. And the North Atlantic deep water is emanating from the North Pole, close to Greenland and North Sea. So that salty and cold water sinks quickly and forms this third layer of colder water underlying the intermediate Atlantic water mass. But the major player among the four is the Antarctic bottom water, starting basically right off the coast of the Antarctic continent in the south, extremely cold, and so it's much denser, and it's probably extremely saltier too. And it sinks in and goes down into the deep ocean water and underlies all these three different water masses. So these different water masses, deep water current systems, have different density structures and different temperatures and salt contents, and that's why they do not mix up much at all. They form these distinct layers. And these two deep currents, the Antarctic bottom water and the North Atlantic deep water, basically are the thermostats of the Earth's climate, because they form these huge deep water, cold water masses, bringing lots of nutrients and dissolved oxygen, but also regulating the ocean water temperatures and climate around the world. Let's take a look at the convection process in the North Atlantic Ocean. South to the right and north to the left. So you can think of this as the coast of Labrador and Greenland. And so what happens is that cold water sinks in the Labrador and Greenland in the north, as just we discussed, and it forms this deep cold water layer, and it generally goes down to about 2,000 meters at depth in the oceans, and bringing cold water from north to south. So because this cold water is sinking from the surface near Greenland, the surface water now displaced and pushed down into the deeper parts of the Atlantic Ocean, has to be replaced by warm water. So the warm water coming from the subtropical regions come to the north and replace the surface water. So there is this convection system in the Atlantic Ocean because of the temperature changes and air-sea interactions. So the deep ocean water is extremely cold. I did dive into the Pacific Ocean, the Atlantic Ocean, and the central equatorial Pacific Ocean. And after about 200 meters, once you pass through the photic zone, the ocean water becomes extremely dark and cold. And once you get below a couple hundred meters, actually, you don't have any wave actions affecting the water at those depths. So we have very still water just affected by deep ocean currents. And as you go deeper, below 3,000, 4,000 meters, the life becomes very sparse, and you have very little productivity unless you have some upwelling zones, and the organisms become very strange. We'll talk about this in biological oceanography later on. You're looking at basically giant eyes and huge claws and tiny mouth in this organism, and they preserve energy by not moving around too much, but basically grabbing any passing by organism as prey. And at these depths, in deep oceans, where deep ocean currents exist, there's extremely high hydrostatic pressure pushing down. We identify deep water masses and deep currents by their temperature and salinity characteristics. So this is a TS diagram, density TS diagram that we talked about earlier. And you're looking at the temperatures increasing from 0 degrees Celsius to 20 degrees Celsius, going up in this direction on the vertical axis. And we have the salinities increasing from left to right from about 33.5 per thousand to 36.5 per thousand ppt. So that's salinity increasing in this direction. So as you remember, temperatures and salt contents in salinity affect the density. So as the temperatures go down in this direction and the salinity is increasing in this direction, along this red arrow, you are increasing the water density with increasing salinity and decreasing temperatures. So these are the higher density regions on this TS diagram. These are lines of constant density, these blue lines. So you can see that in this direction along this red arrow, the density lines are also increasing. They are not straight lines, they are curved lines as we discussed last time, because the changes are not linear in terms of density changes with respect to salinity and temperature fluctuations. So on this TS diagram, I'm showing you 5 major deep water masses and deep water currents. This one here in this light green box represents the Antarctic intermediate water, and this orange parallelogram there shows represents the North Atlantic central surface deep water. And we looked at the diagram earlier, and so you can see where this is sitting as a little sandwich between the two other layers. So if you look at where they are, they're both sitting on the same 1.027 gram per cubic ISO density line curve. So that means that these two deep currents, water masses, have pretty much identical density, but yet if you look at the Antarctic intermediate water mass, you will realize that it's much colder, about on average 5 degrees Celsius, and also doesn't have much of a salinity. And so, and yet the density of this water mass is the same as the North Atlantic Central Surface water mass, which has much warmer temperatures, all the way up to the tune of 15 degrees Celsius from about 8 degrees Celsius. And so it is much warmer, but it is also much saltier. So if you look at the salinity of this North Atlantic Central water, it has a wide range, but it is much more saline than the Antarctic intermediate water. So here, cold temperatures make up for the density of the Antarctic intermediate water, whereas here, the high salt content and high salinity make up for that higher density of this particular water mass. So even though these two water masses have exact same or similar densities, their physical characteristics in terms of temperature and salt contents, they're very different. So this is very important to keep in mind. So that's why these different water masses with different salinity and temperature conditions can keep their identity, and they may not mix up at all. We're looking at this bathtub analogy of the Atlantic water again. Here we're looking at the Greenland in the north and Antarctica in the south, and we have the warm tropical surface waters. Here's that Antarctic intermediate water that we talked about earlier, pretty warm but higher salinity. Higher salinity because that comes from high evaporation rates in the mid-latitudes where it started sinking and forming. So Antarctic bottom water makes up the very cold, the coldest bottom water system. If we zoom into this part of the subantarctic part of the South Atlantic Ocean, we're looking at different zones with different current patterns, deep water patterns, and you see that this is the Antarctic water bottom water current, and sinking from the surface at extremely cold conditions. And then here is the North Atlantic deep water coming in from the north, and then to the north of that we have the Antarctic intermediate water right there with relatively warmer temperatures and relatively less salt content. So as you go from the south to the north, you see the different changing temperature conditions, and the surface water getting relatively warmer. So the temperatures and the salinity contents absolutely affect the deep current systems. The last thing I wanted to show you is the conveyor belt circulation system in the global oceans. So we're looking at the Thermohaline conveyor belt circulation. The blue color shows the deep cold waters, and then the red color shows the warmer current systems. So you see that near off the coast of Greenland and in the Arctic Circle, we have the North Atlantic deep water sinking and flowing at depth towards the equatorial region and crossing to the south, and then converges towards the Antarctic bottom water, and collectively they form the deep cold current system flowing parallel to the Antarctic continental margin and then flowing further to the north, crossing the central Pacific Ocean, and eventually becoming much warmer by the time it reaches these latitudes, and then it continues its circulation as a shallow warm current from the northeastern Pacific Ocean across the equatorial zone, picking up much warmer temperatures and heat, and then continues across from the southern tip of the South African continent all the way to the western part of the Central Atlantic Ocean, and that's where the Gulf Stream now becomes part of this thermohaline circulation, bringing warm water and lots of organisms actually from this region all the way to the continental Europe, British Isles, and the Nordic countries as well. And that's where this water surface current becomes cold and starts sinking and starting again this whole loop of the conveyor belt circulation. So as you can see, these circulation patterns as an artifact of temperature changes and salinity changes really drive the circulation patterns, which in turn affect not just the climate in the oceans, but also in the adjacent continents. Okay, that's the end of the ocean circulation discussion for today, and I hope that you will go into these discussions a little bit in detail later on by yourself and consult with your textbook, and I'll talk to you about other parts of circulation patterns next time. Have a good day.